Hello and welcome to Virtualization for Beginners, module number 1. I'm your host, Kumara Murali. Introduction to Data Center Environment, module number 1. Upon completion of this particular module, you should be able to understand layers of data center infrastructure, types of compute system, virtualizing network, software-defined data center. So let's begin with lesson number 1, data center infrastructure building blocks. In this lesson, you will learn what are the different infrastructure building blocks of any given data center. Yeah, before we start, my first question over here, why are we learning data center infrastructure here? We're supposed to be learning virtualization basics. The answer to this question is another question itself. What are we trying to virtualize? What is virtualization? We'll understand. But first of all, what are we trying to virtualize? Answer to this question again, what is that is very important for any organization? Good. Answer for a question itself is a question here. Right. For any organization, the most important asset is a data. For a hospital, a patient record is an important asset. For a university, student records are important assets. For a company, its business data is important asset. So all these important assets, that is so-called data, where is it stored? Is it in a paper format? No, of course not. Those days are gone. They are stored in a computer, of course, in a digital format these days. So how is this data generated? In a hospital, how is a patient's record generated? When a patient walks in, does some sort of a health check, a record is generated, a lab record is generated, an X-ray image is generated, or an MRI scan is generated, or a student getting enrolled, his record is saved somewhere digitally, or for a business related to any application, the data is generated. So how is it generated? Where that means you need to have some sort of an application. In a hospital, in a lab, you will have some sort of an application which would help you to record the records related to that particular patient. In a university, some application which would help to maintain the records of a student. Similarly, for an organization. Now, where are these applications running? Now, these applications are running on a machine. So, what is that machine? That machine is nothing but a server or a compute system or a host with some amount of CPU on it, a multi-core CPU probably, some amount of RAM on it, maybe a 8 GB or a 16 GB or a 32 GB RAM for that matter. And of course, you need to store data, so you need to have storage, certain amount of storage, probably 500 GB or a 1 terabyte or TB or 2 terabyte or something. So that's where the data is generated and stored. So you have a physical machine, which is a server, which has some application running on it, which generates the data, which stores the data. Now, storing again could be locally stored or it could be externally stored. Okay. So if it's externally stored, you will come across storage devices. We'll speak about storage devices again later. So storage, where the data gets stored by an application, could be local to that server or could be external to that particular server. Like this, there could be many such servers within the hospital or within the university or within the organization of a company where there are different applications running. For example, there could be in a hospital, there could be an application server dedicated for, let's say, for example, generating records related to lab tests, or a separate server related to an MRI or an X-ray or some other kind of a digital device. In a university, yeah, of course, you could also expect a mail server there. You could also expect a file server there. Okay. Similarly, in university also, you could have a mail server, you could have a file server, you could have a database server, could have different servers. Okay. That means for each application, you have a server dedicated. But why? If I have multiple applications on a single server, and particularly if it happens to be a Windows, that is the assumption we have, till date. If there is more than one application running on a machine, for some reason one of the application crashing, it might affect the rest of the applications which are pretty much fine. And also which could completely lead to a disruptive operation in terms of other applications which are functioning fine. So people do not want to take risk here. So what they do is, instead of having multiple applications on a single server, they tend to go for dedicated servers for every individual application which they think is important for them. So what is the problem here? End of the day, you will have multiple servers deployed within your infrastructure. But where? What is that infrastructure we are talking about? So that is data center actually. So data center is a facility within an hospital or within a university or within an organization where you will have these physical machines deployed. So starting from few servers like 5 or 10 servers, you can imagine tens and hundreds of servers being deployed within a data center. It depends on the complexity uh, and the number of applications that are being used by that particular business for that matter. So every server has its own CPU, RAM, storage, and network, as I said earlier. And I also told you every server has only one application running on it, or maybe max 2 applications running on it. But do you think those single single application, or those two applications running on that particular machine would maximum use the CPU, the RAM, and the storage available on it? Absolutely no. What we have seen is, this is the trend that is observed in these kind of dedicated server environment, application server environments. We have noticed that hardly 10% of the underlying resources are used, because the application doesn't need more than that. For an application to function successfully, it doesn't need more than 10% of CPU resource or 10% of the RAM and the 10% of the storage available overall. This is in general actually. Could be little more than that also for that matter. So that means almost 90% of the underlying resources of your server are not being utilized, underutilized. They are underutilized. It's a complete waste of resources actually. And the other factor, one is underutilization of resource. Second factor is, now since you are deploying too many servers, within your data center, you end up consuming too much of real estate space within your data center, and moreover these days the real estate space is very expensive. Okay, so you'll be spending a lot of money for that. The third factor, when these many number of hardware components are running, naturally they would be consuming a lot of electricity. And since these machines run 24/7, they dissipate a lot of heat, and beyond a specific temperature, these devices do not function. So they automatically shut down if they have been built for it, or they may crash if they're not built for auto shutdown. Okay, so you got to have some sort of a temperature control over here so that there's a moderate temperature always maintained, which would help these components to function without failure. So there's a cost involved in terms of procuring your servers, which is known as capital expenditure. Once you procure them, deploy them, you got to maintain them, you got to manage them. So you need to spend a lot of money for this in terms of electricity, cooling, and then manpower. So this is called as operational expenditure. So there's a lot of money getting involved over here, which is a huge cost for a company. More than capital expenditure, operational expenditure is the most expensive thing because it's a recurring cost. Because once you buy these servers, which is a one-time investment, for the next few years, these days 3 to 4 years is what max life cycle of the of servers we consider. So that means for the next 4 years, you got to spend a lot of money for electricity, cooling, uh, humidity control, sensors, and then you got to have manpower to manage and maintain them. There's a lot of recurring costs involved here. So these are some of the biggest challenges faced by any organization in the modern day, right from the beginning, of course. So how do we handle these, things? So that's where we speak about this data center infrastructure, at the very first place, and then we move on to virtualization. So in a data center, we have these components which are placed. Okay, so first component of course is the core component is the compute system or the servers or the host machines. Now since there are multiple servers, you got to have these servers interconnected because sometimes you need to have compute to compute communication, and in certain scenarios you might have an external storage device connected to your compute system to provision storage. So naturally you'll have a networking device between your compute and storage. That's where you have compute to storage connectivity coming in. So networking would be LAN, SAN here. So you have network devices. Even these network devices are physical in nature. They consume a lot of space. They're expensive. Okay, which leads to capital expenditure as far as operational expenditure. And of course, storage, most expensive out of all these three. If you compare physical compute system, network, and storage, the most expensive one is the storage system, of course. So it's a one of the biggest challenge is to handle storage costs. That's the reason virtualization is very seriously taken in a storage environments as well, to save a lot of money in terms of storage. Okay, so since virtualization is applicable to all the three components, that is compute, network, and storage, we are trying to learn data center infrastructure building blocks because these are the components which actually make a data center. Now, how big do you think the data center could be? Usual picture that you get when you speak about data center, if somebody knows what a data center is, uh, they think in terms of a huge space with too many servers and too many connecting devices and huge storage boxes connected. Actually speaking, that's not the case. Yeah, of course, in a large enterprise environment, you might come across such data centers, but actually speaking, a data center need not have to be always big or huge. Even in a small room from where you're right now, listening to me or going through this course, you could set up your own data center. In fact, Believe it or not, I have set up my own data center within my laptop. Forget about the big room where you could have a data center. If you have a good configuration system, a desktop or a laptop with you, you could set up your own data center within it. So that is software defined data center actually, which you will learn, later at the end of this particular course. I mean this module. Uh, I have set up my own data center within my laptop. Okay, where I have compute, virtual computes. I have virtual network as well as virtual storage configured. So just to give you an example, and picture in terms of what a data center is. Remember, a data center need not always have to be huge infrastructure. It can be simple, okay, or it can be too complex as well. Whatever it is. So, what are the building blocks of a data center? Core or the underlying, foundational layer of any data center is the physical infrastructure, where you have physical servers, you have physical networking devices, and you have physical storage. Okay. On top of this physical infrastructure, to overcome the underutilization of these physical resources, you could go for virtual infrastructure. So you are able to overcome all those disadvantages what we understood earlier in terms of physical infra. Underutilization of resources, what we understood, we can overcome that. I said there's huge capital expenditure, operational expenditure involved. You can reduce this with virtual infrastructure. So we will see that. And the core concept that we would learn in this entire course is virtual infra, virtualization basically. And predominantly, since this is a course for beginners, uh, we will only concentrate on compute virtualization. Network and storage are two separate streams when it comes to virtualization, and they are huge in terms of concept and technology. So we have plans to come out with a separate course for compute virtualization and network virtualization and storage virtualization. Right. So the other layer over here is software defined infrastructure, which forms a foundation for our next level of what we have in a physical infrastructure. As I explained earlier, you have compute system, storage, and networking devices. And if you look at all these three, compute, storage, and network, they have their own operating systems, system softwares, and protocols for their function. Okay, if you look at compute system, you can have Windows operating system, you can Linux operating systems, Unix operating systems, and storage devices also would have their own operating systems. Okay, to give you a simple example, um EMC EMC has a enterprise storage box called as VMAX. Uh, that particular box has its own operating system called as Ingenuity. Similarly, EMC has a mid-range storage box called as VNX. So VNX also has its own operating system. Now that is something I would leave it to you to find out what is the operating system or operating environment which is popularly known as of VNX storage box. So like this, every vendor who manufactures storage boxes, they have their own proprietary operating system running on them. Same thing applies for network as well. If you go for a Cisco Ethernet switch, it has its own operating system. If you go for a Cisco SAN switch, it has its own operating system. And of course, all these would have their own protocols also to function. Okay. Virtual infrastructure, I told you why we need this. Virtualization would abstract physical resources and create virtual resources. So in a compute system, the physical resources which are abstracted to create virtual resources out of them are CPU, RAM, network, and storage. I could abstract all these four physical components and create virtual resources out of them. I could create virtual CPU, I could create virtual RAM, I could create virtual network, that is NIC of course, and network storage. So virtual components could be in a data center. The virtual components could be virtual compute, virtual storage, and virtual network, which is created from physical resource pools using virtualization software, of course. So to give you an idea, for compute virtualization from VMware, we have a software called as vSphere. So we use that to virtualize compute systems. For network, we have NSX, and for storage, we have vSAN, VMware vSAN. The benefits of virtualization, of course, resource consolidation and multi-tenant environment, improved resource utilization and increased return on investment, flexible resource provisioning, and rapid elasticity. Rapid elasticity means whenever I want, I can add more and I can even reduce them whenever I feel like. Software defined infrastructure deployed either on virtual layer or on physical layers. Usually it's deployed on a virtual layer. All infrastructure components are virtualized and aggregated into pools through software, where underlying resources are abstracted from applications. So what we do is we use a bunch of APIs to abstract all this, and ultimately it enables us to deliver IT as a service. Centralized, automated, and policy-driven management and delivery of heterogeneous resources. Components of a software-defined infrastructure are software-defined compute, software-defined storage, and software-defined network. So if I'm using hypervisor to virtualize a compute system and provision compute systems using software-defined using vSphere for that matter, that forms a software-defined compute. If I use VMware NSX to provision network or to manage and automate network, that forms a software-defined network. If I use VMware vSAN for provisioning and managing storage, that forms a software-defined storage. Okay. So that way, in a data center environment, we have two different classification of infrastructures. Sorry, best of breed infra and converged infrastructure. So I can set up my own data center in these two approaches. What is best of breed infrastructure? Compute systems, let's say I'm going to buy them from Dell. Network, I'm going to buy them from Cisco. And storage, I will buy it from EMC. Each of these core components of data center purchased from different vendors. That is called as best of breed. So when I integrate them together to set up my own data center, that forms a best of breed, infrastructure, data center infrastructure. Okay. If you go for converged infrastructure, let's say an organization says, I will provide you compute system, I will provide you network, I will provide you virtual platform as well as storage, all put together as a single component, as an integrated package. So that is called as converged infrastructure, where a customer need not have to worry about purchasing, compute system separately, network separately, storage separately, and virtualization separately. Where at the end of the day, he will end up, contacting different vendors for different components when in case of some issues. Okay. So that's one of the biggest challenge that a lot of IT organizations face. I mean, data center administrators face or IT managers face, because sometimes you really don't know where the issue is. So you got to shuttle around different vendors to resolve a specific issue. So that's where this converged infrastructure would help you. One vendor is going to provide you everything: compute, network, virtualization, as well as storage. So single point of contact for any kind of issues. That's the biggest advantage of converged infrastructure. But otherwise, converged infrastructure has its own disadvantage also. You always have this vendor lock-in, because in a converged infrastructure, you don't have a choice to pick in terms of the compute, network, virtualization, or storage. You like it or not, you may have to go for Dell servers. You like it or not, you may have to go for Cisco. You like it or not, you may have to go for EMC, because that's how it is. There's always a vendor lock-in when it comes to converged infrastructure. But otherwise, converged infrastructure will always offer you a pre-configured and optimized self-contained unit. So you don't have to really worry about procuring and deploying and wasting a lot of time in configuring all these things, because they come pre-configured and optimized, self-contained single unit. Best of breed infrastructure would enable you to repurpose the existing infrastructure component. Repurposing nothing but provisioning or using the existing infrastructure components. Converged infrastructures would facilitate faster acquisition and deployment. So there is always uh, more time for you to manage things, because you're able to acquire faster and deploy faster here, right? So that's the end of our lesson number 1, where we understood layers of data center infrastructure, components and functions of each layer, and best of breed versus converged infrastructure. Let's move on to lesson number 2, compute system. This is very simple. You all know what a compute system is. What are the components of a compute system? Just in case you're not familiar with it, we're going to talk about two things: physical and logical components of a compute system and the types of compute systems. Types of compute system is something which you might not be much familiar with. You might have seen one type of compute system. There are basically different types of compute systems available if you're a beginner. Okay. What is a compute system, for example, for that matter? We've been speaking about compute system, host, machine, server all this time. What are they? Any machine, physical machine basically, or it could be virtual machine also, but here we will speak from a physical machine point of view. A machine which has some application running on it. If you speak from a university point of view, it could be a student record database, or it could be a file server, or mail server, or any other application. Could be an CAD system for that matter. So a machine which has some application running on it is a compute system for that matter. Okay. So physical components of any compute system are processor, memory, storage, and I/O devices. And the logical components of any compute system are OS, operating system, of course, Windows, Linux, Unix, Mac, whatever. Device drivers to have to make sure the hardware components within that machine function properly. And then you have file system, and then a logical volume manager. These are the logical components of any compute system. In certain areas, you come across a term called host also being used for a compute system. I usually use the term host to speak about a compute system. Host is a term which is widely used in storage area network environments to represent a server with an application on it. Physical components, of course, I've already spoken about it. Nothing much to speak about this. And the reason why I'm mentioning all this is when you speak about compute virtualization later on, we try to virtualize these components. We will virtualize CPU, we'll virtualize memory, and storage also. Okay, types of compute system. Here we go. I don't know how many of you have come across these things. If you don't know what these types are, tower compute system, rack mounted compute system, or blade compute system, this will be an assignment for you. I want you to Google or do whatever you want and find out what is the difference between these three. Tower compute system. Tower compute system, you would have seen them, you would have used them. Your desktop is an example for tower compute system. Otherwise, rack mounted system and blade compute system, I want you to find out the difference between rack mounted compute system, blade compute system, and the ideal application environments where you would see these used. Okay, please find out and post it on our discussion forum. Okay, so that's an assignment for you. I'll give you assignments like this in every lesson or every module that you're gonna learn. So please try to find the answers for all those assignments. So lesson number 2, we have done with it. Types of compute system: tower, rack, and blade. Okay. Our next module is lesson number 3, which is compute virtualization. I told you why we need to go for virtualization. 3 reasons. Let me summarize again. Utilization of resources. Okay, so we need to overcome this. We need to make sure all the resources are well utilized, maximum utilized. Huge capital expenditure which is supposed to be reduced, and huge operational expenditure which is supposed to be reduced. And of course, I forgot to tell you one thing. Because of huge consumption of power, cooling, and other factors, there's large amount of carbon emission also. So go green is another factor behind virtualization. So your data center should be green. Okay, that's another thing. A lot of people are looking at, green data centers. So virtualization would help you to achieve that. Okay. So compute virtualization is a technique of abstracting the physical compute hardware. What are those hardware components? RAM, CPU, networking device, that is your NIC cards or host bus adapters, and storage. So we are trying to abstract these physical hardware components from the operating system and applications, thus enabling multiple operating systems to run concurrently on a single or clustered physical compute system, right? Let me show you what is that. Here you go. So if you look at this particular animation over here, the outer box, what you see is one physical server with its own set of CPU, RAM, network, and disk. Usually, if you have one single operating system running on it and its applications, these hardware components will be underutilized. So overcome this, what we do, we virtualize. So when you go for virtualization, the same set of hardware resources could be maximum utilized by virtualizing them, where a virtual CPU, virtual RAM, virtual NIC, and virtual storage could be created and provisioned to individual what do you call operating systems that you would create on this particular platform. Now this individual box, smaller boxes within this blue rectangle is actually a single virtual compute system. We call it as a virtual machine actually, right? So an individual virtual machine would have its own operating system with its own applications running on it, where each of these virtual machines, they get their own CPU, RAM, NIC, and storage from the underlying hardware, right? So this is compute virtualization. So what is the advantage over here? If there was no virtualization concept available, then you would have these 3 VMs deployed as physical servers, right? If there was no virtualization available, then you would end up deploying 3 individual physical servers with their own physical CPU, RAM, network, and storage. So imagine the amount of physical space they consume within your data center, the amount of power you need to run them, and the amount of cooling you need to use to cool them. Okay, so there's a lot of capital expenditure and operational expenditure involved, and of course, underutilization of resources. So everything can be overcome with this compute virtualization here. So look at these individual components. This CPU for this particular VM is virtual. So how am I able to give this? That's where we have the software called as vSphere. vSphere is a hypervisor. That's an software using which we are able to abstract these underlying physical resources and provision them as virtual resources to these individual virtual machines. So if this is a multi-core CPU, I could abstract a single core out of this and provision as a CPU to this VM. If there is an 8 GB RAM or a 16 GB RAM or whatever, a certain amount of that RAM can be abstracted and given it as a resource, virtual resource to this VM. Similarly, NIC and storage also. For these individual VMs, these virtual resources would appear as physical components. Remember, so this virtual CPU is a physical, CPU for this VM. Similarly, this virtual RAM is physical for this, virtual machine. Similarly, NIC and storage as well. They don't appear as virtual for them. They appear as physical. Okay. So here is a slide which talks about whatever I explained so far. Before virtualization, you have a lot of IT silos and underutilized resources, inflexible and expensive, management inefficiency, and risk of downtime, which is a big factor. After virtualization, you do a lot of server consolidation and improved resource utilization, flexible infrastructure at a very lower costs, increased management efficiency, and increased availability and improved business continuity. The first 3 points, of course, you would have understood by now, but what does this last point mean? Increased availability and improved business continuity. If you look at this before virtualization, pointer, last point says risk of downtime. That means this entire physical, machine with CPU, RAM, NIC, and storage could be a single point of failure. What if the RAM fails? The entire machine is down. What if the CPU fails? The entire machine is down. What if the storage fails? The entire machine is down. Or the system itself crashing for that matter. So virtualization can overcome that. In case in a virtualization environment, how do we overcome this? You might have multiple such sorry, you know, uh, servers where you have vSphere installed and you have VMs configured on them, which could be clustered together, and you could use some vSphere technologies like HA, high availability, fault tolerance, replication, and business continuity solutions like business, backup and recovery solutions implemented, which would help you to overcome this risk of downtime what we had in physical architecture. We will speak about all these individual components of vSphere, that is HA, fault tolerance, business continuity solution, and replication once we start module number 2, because module number 2 we have a separate lesson where we speak about those individual components. There you will understand how we are able to achieve availability and business continuity with the help of those components. For now, don't worry about all those stuffs. That's end of our lesson number 3 about compute virtualization. Lesson number 4 is about storage and connectivity. One of the very important topics for you to understand. In this lesson, we will speak about evolution of storage architectures, uh, right from server centric approach to storage centric, centralized storage approach. Types of storage devices from magnetics disks to optical disks, compute to compute network, compute to storage network, and certain storage connectivity protocols available. If you look at the evolution of storage architecture at an enterprise level, initially people had this client server architecture where everything was server centric, where storage was local to that particular server. So if I had a server used by sales team for, let's say for example, for some sort of a sales related application, everything is locally stored within that particular server. Similarly, a finance server, everything stored locally within that particular server. So all the storage is local to these servers. So the problem with this particular approach is, in case of this server by itself failing, this entire storage is unavailable. So that's one of the risks we had with this server-centric architecture, because we always had the risk of availability due to downtime scenarios. So that's when we moved from server-centric approach to storage devices. That means storage array approach by implementing storage area network. In storage area network, we are able to overcome that risk of downtime or availability by moving our servers data from local storage to centralized storage machine over a storage area network. So how does a storage device on a storage area network help you to achieve this high availability, which was a big concern in the server-centric approach? These storage devices are primarily designed for availability, with every single component being redundant, right from the CPU, memory, network to the storage devices by themselves. Everything is redundant here. Storage level, protection is achieved using technologies like RAID. RAID is a technology which would help you to recover your data in case of a disk failure. Okay, of course, you could still achieve that on a server-centric approach, but the problem is, remember again, your disk would be local to the servers. So server itself failing, you end up, in a data unavailability scenario. So which could be overcome with this particular approach. Okay, so with the help of RAID, of course, we are able to recover or reconstruct your data in case of a disk failure. And most importantly, your data is always guaranteed to be available because of storage specific redundancy technologies available. Okay, so that's the benefit of going for centralized storage approach. There's lot to speak about storage from a storage area network point of view, but this is not a platform to speak about all those things. I'm trying to, explain in a simplest form possible. So if you want to learn more about storage area network, storage, enterprise storage, probably we need to have a separate course on that. So maybe when we start a separate course on vSAN, we will speak about all the storage related concepts in detail. Okay, but I'm sorry, unfortunately, this is not the platform to dig deep into the storage concepts. Just a general understanding is more than sufficient for us. So what is this storage provisioning? It's a process of assigning storage resource to compute system based on three factors: capacity, availability, and performance requirements. So whenever you want to provision some amount of storage space to a compute system, let's say for example, I have a mail server with Exchange, Microsoft Exchange running on it, or some other mail server for that matter. I have around 1000 inboxes to be configured, where each inbox probably I want to allocate 100 MB of space. So 1000 into 100, you can imagine how much space we need. So where do I get that space from? Of course, you need to have a centralized storage system. So from that machine, I would provision some amount of storage space for this mail server. So that process of presenting that space, that storage to the mail server is called provisioning. Okay, so when we are planning to provision that much amount of space to a server, in our example mail server, there are a lot of factors to be considered. Okay, so we summarize them into three things: capacity, availability, and performance. Keeping these three factors, we will plan and configure our storage system and then provision the storage to the server. So that's where we, think about the type of storage device that I have, whether it is a magnetic disk, whether it is a flash drive, what kind of RAID technologies I'm supposed to implement, because each RAID technology has its own advantages as well as disadvantages in terms of availability and performance factors. So you've got to consider all these factors and then provision the storage. So that way, there are two different ways of provisioning storage, two different approaches. In fact, one is called traditional storage provisioning, the other one is virtual storage provisioning. So this, whether it is a traditional storage provisioning method or a virtual storage provisioning method, The storage, the so-called storage what we provision is a logical device basically, which is popularly called as logical unit number. So in any storage subsystem from any vendor for that matter, the term what we use to represent a logical device is LUN, logical unit number. This LUN is actually a unique number that is assigned automatically to that logical device that is carved out of this so-called storage subsystem. But technically speaking, that device, that logical device what you carve out of the storage subsystem is called SCSI device, which is logical, of course, like a partition that you create out of your hard drive. You have a physical hard drive on your laptop or desktop. You break it in logical, drives, partitions like C, D, E, F, whatever. Similarly, out of a bunch of hard drives from a storage subsystem, we carve out, a space that is known as logical unit number or a SCSI device. So that is what we provision to a host. And this LUN can be an entire physical disk, could be part of a disk, that is a slice out of a single disk, or it can be an entire disk array or part of a disk array. Okay, usually it is usually part of an disk array. You will never come across LUN created out of a single disk or a LUN created out of a part of a single disk. It is usually part of a disk array. So how do we visualize this? Take this example on the screen. There are three physical disks, disk 1, disk 2, disk 3, each 100 GB in capacity. Now I have logically pooled these three 300 GB hard drives together and built a RAID protection on top of it, so that even in case one of the drive fails, I will be able to rebuild it. Okay, and how do we rebuild using RAID? That is something you need to explore. So find out what are the different RAID protections we have, RAID levels that we have, using which we are able to protect our data in case of disk failures. So I would use one of them, one of the RAID protections here to protect my data from disk failures. There's a server here, probably a mail server. It needs certain amount of space to store the data. Okay. Maybe he's looking for this is just an example. Okay. So don't think practically this is the case everywhere. Could be more than this also. So in this case, I'm going for a 30 GB disk space. So I need 30 GB space, storage space for my mail server to store the data, my inboxes. Okay. Now since going by a single disk could lead to a downtime in case of a disk failure, we go for RAID protected pool of disks here. So out of this RAID protected pool of disks, I'm supposed to carve out 30 GB space. Okay, where this 30 GB will be evenly spread across all the three disks within this RAID protected pool of drives. So the advantage here is, in case one of the disks failing, the part of data which I lose because of the drive failure, I could easily reconstruct it using the available RAID protection. Okay. So considering that fact, let's create a 30 GB hard drive here. Look at this. There's a slice of space taken from each disk within the RAID protected pool of drives. Since it is 30 GB, let's divide this into 10 GB each. So from disk 1, I get 10 GB. Disk 2, you get 10 GB. And disk 3, you get 10 GB. Thus forming a single logical device of 30 GB capacity. Okay. And I would provision that to the server. How do we provision this LUN to the server? Where my server is an individual component and my storage is an individual component. So that is where we have storage concepts which you will learn if you take up a storage related training. Okay. So thus a 30 GB logical device is presented to a server from an external storage. So what is the storage provisioning in that case? This 30 GB what is presented to the server could be used as a single block device by the server at any given point of time. So that means the entire 30 GB is physically allocated to the server. It has been allotted to the server where the server would see that 30 GB as a single drive. For him, it's a hard drive of 30 GB capacity. And what does a system do when it identifies a raw device? Remember, this 30 GB is a raw device now. It's an unformatted drive space, a single drive space for the server. Can you write anything onto a raw device? No. Only on a formatted device you can write. The same thing applies in this scenario also. A server is looking at a raw device of 30 GB capacity. Now he is supposed to format it. If it's a Windows platform, you will have a Windows logical volume manager sitting on it. He would do the formatting and he will put the operating system signature on it. So that forms a file system. It could be an NTFS or a GPT. If it's a Unix, if it's a Linux, it could be ext2 or ext3 written on top of it. Okay. Similarly, different operating systems have their own file system signatures to write after formatting. Once formatted, this 30 GB disk space is now available as a single unit for the server to write. So this is called traditional provisioning. Everything is fine, but there is a problem with this approach. The problem is I gave 30 GB to the server, but the server has hardly written some, let's say, 5 GB. Okay, for the past few months, he's hardly used the rest of the space. So that means the rest 25 GB of space is underutilized. It's been wasted by the server. Now remember, in a centralized storage environment, storage is very, very expensive. This is not something like you go to a local market, buy a hard drive and plug it in. It's very, very expensive. There's a lot of approvals and then processes involved in procuring storage here. So underutilization of storage is a offense, if you ask me, in a storage environment. So that's one of the biggest problems faced in a storage environment by the administrators today. So we got to overcome this. What if there are many servers which are underutilizing the storage? They're not that often using the storage space given to them. Okay, they're not that highly transactional, you could say, when it comes to generating data. They hardly write data onto the storage space. So in such scenarios, traditional provisioning is not a good choice because you will be wasting a lot of space here. So you could see this picture on the right hand side over here, a practical example in terms of what happens in a traditional storage provisioning environments. We have an example of a storage system with 2 terabytes of capacity, overall capacity. The entire storage system is going to give you 2 terabyte. Just an example again, storage systems would give you more than 2 terabytes, in fact, in terms of hundreds of terabytes. So 3 LUNs have been provisioned, could be for 3 different servers or one server alone. Okay, so one LUN, first LUN number 1 is 500 GB. Out of 500, hardly 100 GB is written. The rest 400 GB allocated unused capacity. Remember, in a traditional provisioning environment, once a LUN is provisioned to a server, the server is going to format the entire disk space. So that means whatever unused space what you have is completely dedicated to that particular server. There is no way you can take it back. There's no what you call releasing of that space here. Once allocated. So the 400 GB is completely wasted. Similarly, LUN to 550 GB, only 50 GB written, the rest 500 GB allocated unused capacity. LAN 3 800 GB, only 200 GB written, rest 600 GB allocated, unused capacity. So out of what 1.8 terabyte of storage that is provisioned, hardly 350 GB is being written. Actual data is being written. The rest 1.5 GB of 1.5 terabyte of space is allocated but not being used. Remember, allocated but not being used means it is on the server side. So there is no way I can use that for additional provisioning. Okay. So what is available for additional provisioning on the storage side is only 150 GB. That means if one more server needs space, I can only provision 150 GB. There is no way I can provision more than that. Now the question is, there is so much of space lying on the server side unused. Why can't we take it, and use it? In a traditional provisioning environment, that is the problem. You cannot take it back. Okay, once provisioned, it is provisioned. So in this case, additional space, if you need more space, you don't have any other choice but to purchase more space. So purchasing means you need to spend a lot of money, which is a bigger problem. That is where you go for thin provisioning or virtual provisioning method. Okay. So what is this thin provisioning or virtual provisioning concept? A host needs 500 GB. We will give him 500 GB. But this 500 GB is not physically allocated from the storage end to the host. It is virtually given. If it is virtually given, where will the host write? Where will those writes go written by the server? So that is the beauty of this thin provisioning concept. The actual provisioning of space will happen only when the server writes. Okay. So out of this 500 GB, not even a single byte is actually given to the host at the first place. So that means the entire 500 GB is still available on the storage subsystem. Okay. The moment the host starts writing, and of course the host will not write hundreds of gigabytes in one shot, right? It might write in terms of few megabytes to maybe 1 or 2 gigabytes. Okay. So whenever he starts writing, that is when the actual allocation will happen. It's for example, the first block that will be allocated would be 1 GB. Once he consumes that 1 GB, another 1 GB block allocation would happen. Once he consumes that second 1 GB, another one block will be allocated. Thus, block by block or chunk by chunk allocation would take place when the server needs. So this process is called as thin provisioning or virtual provisioning, or very popularly known as on-demand provisioning. So let's understand this with a simple animation over here. Here's a server, he needs 30 GB. Now assuming that he might not utilize the entire 30 GB in one shot, I would do a virtual provisioning to him where I will give him a 30 GB drive space, not physical, but virtual. The moment he starts writing, that is when the actual provisioning of space from my storage would happen. Okay, so how does that happen? Let's see. So again, the same example of 3 hard drives, 100 GB each, with the RAID protection. Now a LAN of 30 GB is to be given. So we will carve out slices of 10 GB each from these 3 disks and create a 30 GB LAN. Here you go. So this green color what I've used here is to represent virtual actually for this particular thing. So here it means all these 10 GB blocks what has been provisioned forming a 30 GB drive space is completely virtual at the first place. So this entire 30 GB disk is virtual, which is presented to the host. Of course, for a host, remember, for a server, it would appear as a single hard drive of 30 GB capacity. it is completely transparent to the host. He never understands that it is, he never would know that it's completely virtual. Okay, for him it will appear as a single physical disk space of 30 GB, though from the backend it is virtual. So when does he actually get the space from the backend? Only when he writes. So if the server does not write at all, that means there is no space allocation happening from the backend. Okay, let's say he writes 1 GB or even 1 MB or 2 MB or something. Now, a 1 GB slice allocation would happen. Let's say there's a policy defined within the storage system which says let the block allocation, physical block allocation happen at a size of 1 GB each. So the moment the first write comes in from the server, a 1 GB slice will be allocated from the backend to the servers. So now, out of 30 GB, the actual physical block space what he gets is only 1 GB. The rest 29 is still available on the storage side, which I could still use for provisioning one more LUN to another host for that matter, or for the same host for that matter. So thus you are able to save 29 GB of space, which could be well utilized for other applications. The same thing is explained over here, and on our second picture over here, virtual provisioning. The same storage system of 2 terabytes, 500 GB, 550 GB, and 800 GB LUNs provision, which are virtual in nature. 100 GB written on first LUN, 50 GB on second, and 200 GB on the third LUN. Actual space that is consumed is 350 GB. The rest of the space, which is 1.6 terabyte, is logically been presented but physically still available on the storage system itself. So here, whichever LUN needs space would be provisioned from this available 1.65 terabyte itself. So in case none of these hosts, none of these LUNs are writing data, this 1.65 terabytes is never wasted. It is still available for new LUNs to be created, given to new servers. Thus, available capacity of terabyte, 2 terabyte, available capacity of 2 terabyte is well utilized with the help of virtual provisioning. Types of storage devices. Where do I store data? What kind of devices do I use to store my data? It could be magnetic disk drives, where it could be your traditional SATA drives, or it could be SAS drives. Okay, in enterprise storage environments, we tend to use SAS drives popularly. Okay, it could be 10K RPM drives, 15K RPM drives, or it could be 7.2K RPM drives, but they're all magnetic disks, remember. So there is a lot of mechanical movement here. So performance wise, not great. So if you're really concerned about performance, you need to go for solid state flash drives, which are designed for performance, but they are expensive. And the other type of storage devices that you tend to use is magnetic tape drives. Magnetic tape drives uh, are primarily used for backup environments. Okay, to store your data, to take a backup of your data onto the tapes. But the problem with this tape drives is they are sequential data access. They use sequential data access. So fetching data is very slow because you need to do to and fro movements across forward and backward movements for fetching the data. But it's a very low cost solution for long term data storage. So if you are planning for archiving huge amount of data or to back up huge amount of data at a regular interval, the very cost effective option is magnetic tapes, very widely used in organizations. And the last option is optical disk drives, which are used for, of course, personal use, not for enterprise environments. It's a very low cost option for long term data storage, but less reliable ones. Okay, so storage, what are the different ways in which storage can be virtualized? We have something called as virtual volumes. The LUNs what we understood so far is nothing but virtual volume concept. And we also have something called virtual disk files, which are widely used in compute virtualization environments. And we also have something called as virtual storage systems. And storage virtualization software can be built into the operating environments of a storage system. Um, as a spoke about EMC, Vmax, and VNX. So these storage devices have this virtualization software built into them. You do not have to install them as a separate software as such. In certain environments, you would have virtualization software, storage virtualization software installed on an independent compute system. This is something which you would come across in a software-defined, environments. And then you also have storage virtualization software built into hypervisor. Example, VMware vSAN. Now, talking about network, introduction to connectivity. This is a picture which speaks about compute-to-compute connectivity, where you have a set of clients connected to a Ethernet switch, and you have a set of compute system connected to a switch, and both interconnected through a router, thus forming a network of compute systems. And then we have compute to storage connectivity here. Um, uh, Let me just explain this with a drawing here. Let me use a pen. So there are two primary components that you're seeing here, host bus adapter and the storage. So we are trying to connect this host bus adapter and storage through a network connectivity. So what is this host bus adapter? This is similar to a NIC in your regular systems, but this is primarily a networking device used in a host which is connected to a storage area network. Okay, so imagine this as a compute system. So you have this host bus adapter. It's a networking device which has a port. If this is a fiber channel adapter, host bus adapter, this port is a fiber channel port, and this cable what we use over here is OFC, optical fiber cable. And on the storage also, if this is your array, this port here is a fiber channel port, and it could be part of a larger adapter with multiple ports on it, right? And the protocols would define the formats of communication between these devices. So if this compute system over here happens to be a fiber channel host, and the network happens to be a fiber channel network, then the protocol used over here is FC. And if this happens to be an Ethernet environment with Ethernet cable and RJ45 port over here and the NIC over here, then the protocol is an iSCSI protocol. So that's how in a compute to storage environment we use fiber channel and iSCSI, and of course there's one more called as FCOE as the protocols for communication purpose. If you look at the storage connectivity protocols, we initially used to use IDE ATA. Right. In the older PCs, if you have noticed, you have that bus cables connecting from your motherboard to the hard drive, and then one more cable connecting to the floppy drive or a CD-ROM if you have. So that is IDE ATA connectivity. which is purely parallel. Okay, um, because of the limited amount of throughput that it used to provide, we moved on to serial ATA, which used to provide us 16 Gbps of data transfer rate. Then we came across SCSI, which is still being used as a very popular storage protocol, popular standard for compute to storage connectivity. The advantage with SCSI compared to serial AT and other networking connectivity protocols, storage connectivity protocols, is SCSI can support up to 16 devices on a single bus, and it can provide you a data transfer speed of up to 640 Mbps, megabytes per second. Remember. And then storage environments, SAS became very popular, uh, which is used as a point-to-point serial protocol, which replaces parallel SCSI completely, which support data transfer rates up to 12 Gbps, which is 12 gigabits per second with SAS 3.0 version. Very popularly used in enterprise storage environments, SAS, because of its serial nature of point-to-point connectivity and transfer rate of up to 12 Gbps, which is pretty much high speed. And then for a what do you call compute to storage connectivity, the most popular protocol that we use is fiber channel, because fiber channel is considered to be the most reliable and which is going to provide you very high speed connectivity option compared to other protocols, which again provides you a serial data transmission that could operate over a copper wire or optical fiber, very widely on a optical fiber, very widely used on an optical fiber compared to copper wires. And the latest version, the maximum speed, the current speed, the maximum speed at which it could operate is 16 Gbps. Till recently, till last year, it was only 8 Gbps speed what it could support. Now it can support 16 Gbps of speed. And the other option that we have is IP, most widely used and very popular. But compared to fiber channel, IP is not that reliable, but it is a very cheaper option, when you compare to FC. So examples for storage connectivity protocols, which is IP based, is iSCSI and iSCSI, FCIP, and we have one more called as FCOE. So network virtualization is where you try to abstract physical network resources to create virtual network resources in the form of virtual switches, virtual LANs, virtual SANs, and network virtualization softwares which are used to do this can be built into the operating environment of a network device, or it could be installed on an independent compute system or built into a hypervisor. VLAN is an Ethernet concept of network segmentation, which can be used to break up a very large LAN into smaller virtual LANs. This may be useful to control network traffic such as broadcasts. Otherwise, you'll always have a single broadcast domain. If there were no VLANs, you would need one switch for each broadcast domain. That's what we understood earlier. So again, imagine cabling involved and also the potential number of NICs required at the host level. So first, VLANs allow you to have multiple independent layers to construct within the same switch. Earlier example, we saw there's a network segmentation here. Now the question is, if a device, let's say H1 itself, an example over here, is trying to send some packet across the network. Now remember, H1 is connected to the same physical switch as H3, which is on VLAN 30, or H5, which is on VLAN 20. Now, how does your switch deliver that particular packet coming out of H1 to a device which is part of the same segment as H1? That means it is supposed to be delivered to H6, H7, or H2 only. Okay, so that is where tagging comes into picture. Whenever H1 has to send across something out of right, onto the network, it would tag its packet saying that this particular packet is supposed to be, reaching a device which is part of the same segment as I am. So H1 is part of VLAN 10. That means it is supposed to be accessed by a device which is part of VLAN 10 only. So to help your switch understand this, H1 would tag its packet whenever it is sending out some packets onto the network. Same thing would apply for VLAN 30 and VLAN 20 devices also. So that's where tagging is useful. So VLAN tagging is the practice of inserting a VLAN ID into a packet header in order to identify which VLAN the packet belongs to. More specifically, switches use VLAN ID to determine which ports or interfaces to send a broadcast packet to. So a tagged packet contains VLAN information in the Ethernet frame. A typical use case would be if you have one port from a router to a switch with multiple customers attached to it. If you're still confused with that, let me give you a simple analogy. Uh, if you're traveling by flight, if you have an experience of flying, um, whenever you check in your baggage, you get a boarding pass with that you know tag which is stuck onto the back of your boarding pass. Now, what is the use of that particular sticker which is stuck onto the back of your boarding pass? Once you reach your destination, the check-in baggage is supposed to be collected. So you go to a specific conveyor belt in the airport, from where your baggage could be collected. Now, once you reach the conveyor belt, you would see there are many such baggages with a similar make, similar color, which are completely identical to yours. Now, which one will you pick? So that is where the tag which is stuck behind your boarding pass will be helpful for you. So you look at that particular sticker. There's a number with a barcode on it, a barcode. You look at the number, collect your baggage, cross verify with that particular thing. If the number matches, you collect your baggage and walk out of it. So that is a classic, analogy I could give, to make you understand tagging. Okay. So same thing applies for your virtual environment also, in a network environment also. When there are a lot of packets moving across the network, where your network is segmented, if the packet has to be delivered to the right destination, the packet should carry the tag along with it. The same concept applies to storage area network also, where a fiber channel switch could be divided into logical segments called as vSANs, where each vSAN could have its own end devices, connecting devices, like a bunch of host machines and storage devices connected to it, thus forming a separate network. You could also have multiple such logical switches interconnected, thus forming a virtual fabric also. And vSANs would allow traffic to be isolated within the specific portion of storage area network, just like our broadcast domain in VLAN. And ports within a single switch can be partitioned into multiple vSAN, despite sharing hardware resources similar to VLAN here. Okay. So that's the end of our lesson number 4, where we understood the evolution of storage architecture from server-centric to storage-centric, and types of storage devices like magnetic, flash, tapes, and optical, compute to compute and compute to storage connectivity, and storage connectivity protocols. Let's move on to lesson number 5, which is software-defined data center. Software-defined data center uh, is an extended, concept of your virtualization, such as abstraction, pooling, and automation, which is spread across your entire data center resources like compute, network, as well as storage, which would help you to provide services as IT, like IT as a service. In a software-defined data center, all the elements of the infrastructure, that is network, compute, and storage, are virtualized and delivered as a service. where each component is provisioned, operated, and managed through an application programming interface, which is basically another layer which sits on top of your software-defined, architecture. I mean, software-defined layer, and this would form the first step towards. The software-defined compute actually forms the first step towards your software-defined data center. So traditionally, we have been using the software-defined compute concept, but later on, we slowly moved on to software-defined network and then software-defined storage. Now, software-defined network and software-defined storage are gaining more and more popular in the data center environments. Okay, so the components that comprise any software-defined data center include the following: that is compute virtualization, which is being there right from the beginning, and then we have software-defined networking, which includes network virtualization. Then we have software-defined storage, which includes storage virtualization. The commonly seen benefits, most widely seen benefits of software-defined data centers include an improved efficiency from extended virtualization throughout the data center, increased agility from provisioning applications quickly, completely agile. You can quickly provision compute, quickly provision network, quickly provision storage in your environment, and then improved control over application availability and security through policy-based governance. So, software-defined data center, uh, most important thing about it is it is completely policy based process. It's completely policy driven concept and highly automated. Everything is automated here. So as an administrator, you need not have to have an expertise in terms of the compute or the network or the storage which is behind your software layer. You can easily go ahead and provision all these components quickly, and of course the flexibility to run new and existing applications in multiple platforms and clouds. So, and the end result of this entire process is an IT can achieve significantly more at a dramatically lower cost through virtualization. So that's what you are able to achieve through software defined data center. Definition first, and software-defined data center is nothing but an architectural approach to IT infrastructure, that is compute, network, and storage, that extends virtualization concepts such as abstraction, pooling, and automation to all of the data center's resources and services to achieve IT as a service. So compute, storage, network, security, and availability services are pooled and delivered as a service, where SDDC services are managed by very intelligent policy driven software, and this is regarded as the foundational infrastructure for any cloud transformation. This is an abstract view of a data center architecture. As you can see, you have your physical resources, the compute, storage, network. Through the help of certain APIs, you're able to you know uh, uh, what is that virtualize these things, and you can define them as software components using software defined compute controllers, software defined storage controllers, and software defined network controllers, and then provision those things seamlessly to the applications on the end user side, okay, through a set of APIs. Again, software defined controllers discovers nothing but the intelligence behind a software defined component, software defined compute, or a software defined network and software defined storage, which would discover the underlying resources and provide an aggregated view of resources that helps you to abstract the underlying hardware resources and pool them as a single unit. It enables rapid provisioning of resources based on predefined policies. You can define policies in terms of how You need to provision compute system, how you want to provision network, and how you want to provision storage. Based on the policies what you define, the provisioning will happen automatically. It enables to apply policies uniformly across the infrastructure components, all from a software interface itself. It also provides interfaces that enable applications external to the controller to request resources and access them as a service. So that is how you're able to provide, you know, platform as a service, infrastructure as a service, with the help of software defined controllers. So key benefits as understood earlier: agility, purely highly agile, where you can provision services on demand as a service, and then faster resource provisioning, cost efficiency. You're able to save a lot of money in terms of capital expenditure because you're virtualizing all the resources here. Improved control because of policy based governance, automated business continuity, and disaster recovery. Support for operational analytics. So when you speak about automated business continuity, you're talking about backup and recovery solutions which can be automated. At regular intervals, I can back up my underlying resources, whether it is compute, network, or storage. You don't have to sit there, monitor, and then take backup manually. In case of an entire site, going down, also with the help of DR, you're able to recover your entire production site and start operating it on a different site, secondary site, using DR. Then we have centralized management, which is unified management platform for centralized monitoring and administration. Remember, your underlying resources, that is compute, network, as well as storage, will have their own respective management softwares, which are vendor specific. So it becomes very difficult for an administrator to manage them because he has to, specialize on those components. So when you go for software defined architecture, everything can be unified and presented as a single management window, irrespective of the vendors, compute, network, and storage. So you can centralize everything and monitor and administrate these components. Flexibility with the use of commodity and advanced hardware technologies, and the hybrid cloud support. So that's the end of our lesson number 5. What we have learned in this lesson is software defined data center architecture, software defined controller, and the benefits of software defined architecture. Now we have understood what is a data center, what components we have, and what we virtualize here. Now let's try to understand what are the products that VMware provides, to help you achieve these virtualization concepts. For compute virtualization, we have VMware ESXi, nothing but vSphere actually, and then for application virtualization, which we haven't spoken actually, maybe in our second module we will speak about it. We use VMware ThinApp, and for desktop virtualization, which is again we will speak in module number 2, we have VMware Horizon. And for network virtualization, we have VMware NSX, very, very popular in the market today. And then for storage virtualization, we have VMware vSAN. Uh, I would request you to explore all these things whenever you have time and understand what these things are, and get back to me if you have any doubts. Just an what do you call few important points related to these products. ESXi is a bare metal hypervisor. TNAP is an application virtualization solution. What we have vSAN, of course, which is missing over here, which is used for storage virtualization. Okay, so that's it. That's the end of our module number 1. I hope you enjoyed this. You understood the concepts what were taught so far. Any questions, any queries, please post it on our discussion forum. I will answer your questions, or you can mail me. I'll you have my personal email ID, or you can post your questions on my Facebook page or on LinkedIn. That's it. time to take your quiz. Please answer these questions. And thanks for listening. Hope to see you again for our module number 2, where we speak about virtualization. Okay, that's it for now. Thank you very much. Have a nice day.